To determine the appropriate wire size for a long-distance 20 amp ground fault circuit interrupter (GFCI) circuit, it's essential to understand voltage drop in the National Electrical Code (NEC) guidelines. The NEC permits a maximum voltage drop of 3% for lighting circuits and 5% for general-purpose circuits. Let's calculate these allowable voltage drops for a 120 volts 20 amp circuit. For a 3% voltage drop, we multiply 20 amps by 120 volts by 0.3, which equals 7.2 volts. For a 5% voltage drop, we multiply 20 amps by 120 volts by 0.5, which equals 12 volts. These calculations indicate the maximum voltage drop allowed to remain within NEC standards. When running long circuits, upsizing the wire gauge is often necessary to mitigate voltage drop. While the NEC doesn't mandate upsizing every 100 feet, it does require selecting a wire size that keeps voltage drop within acceptable limits. In this scenario, we have a 300-foot circuit with a load of 14 amps, but we must also consider the startup amperage of the pump, which is 20 amps. Factoring in a 20% safety margin for the startup current, we need to size the wire accordingly. To achieve a 3% voltage drop, or 7.2 volts, a number 6 American wire gauge (AUG) wire is recommended. To achieve a 5% voltage drop, or 12 volts, a number 8 AWG wire could be used. However, given the circuit's length and the load approaching the maximum amperage, using a number 6 AWG wire is advisable. This larger wire size will ensure minimal voltage drop, promoting the reliable operation of both the water pump and the low voltage lights. Choosing the correct wire size is critical for safety and performance. Undersized wires can lead to overheating, reduced efficiency, and potential equipment damage. By following these guidelines and consulting the NEC, you can select the appropriate wire size for your specific application. In practice, several factors influence the selection of wire size beyond basic voltage drop calculations. These factors include ambient temperature, the type of insulation, and whether the wires are bundled together. Higher ambient temperatures reduce the ampacity of wires, meaning they can carry less current safely. Similarly, different insulation types have varying temperature ratings affecting their ampacity. When wires are bundled together, their heat dissipation is reduced, also lowering their ampacity. The NEC provides tables, such as Table 310.15b16, that list the ampacity of different wire sizes based on these factors. Always consult these tables to ensure the wire you choose can safely handle the load current under the specific conditions of your installation. Additionally, consider the type of wiring method used. For example, running wires through a conduit can affect their heat dissipation compared to open-air wiring. The NEC has specific requirements for different wiring methods, so it's crucial to adhere to these guidelines. Furthermore, be aware of local electrical codes, which may have additional requirements or restrictions beyond the NEC. Always check with your local electrical inspector to ensure your installation complies with all applicable regulations. When making connections, use appropriately sized connectors that are listed for the wire size and type. Poor connections can cause resistance, leading to heat buildup and potential fire hazards. Ensure all connections are tight and secure. Consider using antioxidant paste on aluminum wire connections to prevent corrosion, which can increase resistance over time. Remember that ground fault circuit interrupters, GFCIs, are essential for protecting people from electrical shock, especially in wet locations like near a pond. Ensure the GFCI is properly installed and tested regularly to verify its functionality. When working with electricity, always prioritize safety. Turn off the power at the breaker before working on any electrical circuits. Use appropriate personal protective equipment, PPE, such as insulated gloves and safety glasses. If you're not comfortable working with electricity, hire a qualified electrician to perform the work. They have the knowledge and experience to ensure the installation is done safely and correctly. In summary, calculating voltage drop, considering ampacity dating factors, adhering to NEC and local codes, using proper connectors, and prioritizing safety are all essential steps in selecting the correct wire size for a long-distance GFCI circuit. By following these guidelines, you can ensure the reliable and safe operation of your water pump and low-voltage lights. Let's delve a bit deeper into the practical aspects of calculating voltage drop and selecting the appropriate wire size. Firstly, it's important to accurately measure the distance of the circuit run. This measurement should include the total length of the wire from the power source to the load and back. Remember to account for any bends or turns in the wire, as these can add to the overall length. Secondly, determine the actual load current that the circuit will be carrying. While the nameplate rating of the water pump may indicate a certain amperage, it's often helpful to measure the actual current draw using an amp meter. This will give you a more accurate picture of the load in the circuit. Thirdly, consult the NEC tables for wire ampacity. As mentioned earlier, Table 310.15b16 provides ampacity ratings for various wire sizes based on insulation type and temperature. Make sure to select a wire size that has an ampacity greater than the load current, taking into account any dirtying factors for ambient temperature or bundling. Fourthly, use a voltage drop calculator to determine the expected voltage drop for different wire sizes. There are many online voltage drop calculators available that can simplify this process. These calculators typically require you to input the voltage, current, distance, and wire size. They will then calculate the voltage drop as a percentage of the source voltage. Fifthly, compare the calculated voltage drop to the allowable limit specified by the NEC. If the voltage drop exceeds 3% for lighting circuits or 5% for general-purpose circuits, you'll need to upsize the wire. Sixthly, consider the cost of the wire. Larger wire sizes are generally more expensive than smaller ones. However, the cost of using a larger wire may be offset by the improved performance and efficiency of the circuit. Seventhly, factor in the ease of installation. Larger wires can be more difficult to work with, especially when running them through conduit or making connections in tight spaces. If you're not comfortable working with larger wires, you may want to consider hiring an electrician. Eighthly, think about future expansion. If you anticipate adding more loads to the circuit in the future, it's a good idea to select a wire size that can handle the increased current. Ninthly, document your calculations and wire size selection. This will be helpful for future reference and for troubleshooting any problems that may arise. Finally, always double-check your work and verify that your installation complies with all applicable codes and regulations. Remember that electrical work can be dangerous, so it's always best to err on the side of caution. Let's also consider some alternative approaches to mitigating voltage drop. One option is to increase the voltage of the circuit. For example, instead of using a 120-volt circuit, you could use a 240-volt circuit. This would reduce the current required to deliver the same amount of power, which in turn would reduce the voltage drop. However, this approach may require additional wiring and equipment, such as a step-up transformer. Another option is to use a dedicated circuit for the water pump and lights. This would ensure that the circuit is not overloaded and that the voltage drop is minimized. A dedicated circuit would also provide better protection against electrical faults. A third option is to install a local power source near the water pump and lights. This could be a small generator or a battery backup system. This would eliminate the need to run a long circuit from the house and would eliminate voltage drop altogether. However, this approach may be more expensive than simply upsizing the wire. A fourth option is to use a voltage regulator. A voltage regulator is a device that maintains a constant voltage output regardless of the input voltage. This would ensure that the water pump and lights receive the correct voltage, even if there is voltage drop in the circuit. However, voltage regulators can be expensive and may not be necessary in all cases. A fifth option is to use a power line conditioner. A power line conditioner is a device that filters out noise and interference from the power line. This can improve the performance of the water pump and lights and can also reduce voltage drop. However, power line conditioners are typically used for sensitive electronic equipment and may not be necessary for water pump and lights. A sixth option is to use a smart home system to control the water pump and lights. A smart home system can monitor the voltage at the water pump and lights and can automatically adjust the voltage to compensate for voltage drop. This can ensure that the water pump and lights always receive the correct voltage. However, smart home systems can be expensive and may not be necessary for all applications. A seventh option is to use a wireless control system for the water pump and lights. A wireless control system can eliminate the need to run wires to the water pump and lights, which can reduce voltage drop. However, wireless control systems can be unreliable and may not be suitable for all applications. An eighth option is to use a solar-powered water pump and lights. A solar-powered system would eliminate the need to connect to the grid and would eliminate voltage drop altogether. However, solar-powered systems can be expensive and may not be suitable for all climates. A ninth option is to use a low-voltage lighting system. Low-voltage lighting systems use a transformer to step down the voltage from 120 volts to a lower voltage, such as 12 volts or 24 volts. This can reduce the current required to power the lights, which in turn can reduce voltage drop. However, low-voltage lighting systems require a transformer and may not be suitable for all applications. Finally, a 10th option is to consult with a qualified electrician. An electrician can assess the specific situation and recommend the best solution for mitigating voltage drop. They can also ensure that the installation complies with all applicable codes and regulations. In addition to the above, consider the impact of harmonics on the circuit. Harmonics are distortions in the electrical waveform that can increase the current flowing through the wires, leading to increased voltage drop. Electronic devices, such as variable frequency drives, VFDs, and LED lighting can generate harmonics. If harmonics are present, it may be necessary to use a larger wire size or to install harmonic filters. Furthermore, consider the impact of electromagnetic interference (EMI) on the circuit. EMI is noise that can interfere with the operation of electronic devices. Long wire runs can act as antennas, picking up EMI from nearby sources. If EMI is a concern, it may be necessary to use shielded cable or to install EMI filters. Also, consider the impact of surge voltage on the circuit. Surge voltage is a transient voltage spike that can damage electronic devices. Long wire runs can be susceptible to surge voltage from lightning strikes or other electrical disturbances. If surge voltage is a concern, it may be necessary to install surge protection devices. Moreover, consider the impact of ground loops on the circuit. Ground loops occur when there are multiple ground paths in a circuit. This can create unwanted current flow, leading to noise and interference. To avoid ground loops, it's important to use a single-point grounding system. Finally, consider the impact of corrosion on the circuit. Corrosion can increase the resistance of electrical connections, leading to increased voltage drop. To prevent corrosion, use corrosion-resistant materials and apply a corrosion inhibitor to all electrical connections. Let's also talk about specific types of water pumps and lights that might be used in this application. Submersible water pumps are designed to be submerged in water. They are typically used for pumping water from ponds, wells, and other sources. Submersible pumps are available in a variety of sizes and flow rates. Surface-mounted water pumps are designed to be mounted above the water level. They are typically used for pumping water from swimming pools, spas, and other sources. Surface-mounted pumps are also available in a variety of sizes and flow rates. Low-voltage landscape lights are designed to operate at a lower voltage than standard 120 volts lighting. They are typically used for accent lighting, pathway lighting, and other outdoor lighting applications. Low-voltage lights are safer than standard voltage lights and are also more energy efficient. LED landscape lights are a type of low-voltage landscape light that uses light-emitting diodes, LEDs, as the light source. LED lights are very energy efficient and have a long lifespan. They are also available in a variety of colors and styles. Halogen landscape lights are another type of low-voltage landscape light that uses halogen lamps as the light source. Halogen lights are brighter than LED lights, but they are also less energy efficient and have a shorter lifespan. Solar-powered landscape lights are a type of landscape light that is powered by solar energy. Solar lights are very energy efficient and do not require any wiring. However, they may not be as bright as other types of landscape lights. In addition to the above, it's also important to consider the aesthetics of the installation. Make sure to choose a wire and conduit that blends in with the surrounding landscape. You may also want to consider using a decorative junction box to conceal the electrical connections. Finally, remember to obtain all necessary permits before starting any electrical work. The electrical work is typically regulated by local building codes and may require a permit. Failure to obtain a permit can result in fines and delays. The information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician before starting any electrical work.